All right. Up next we have. Oops. Up next we have Devran. Sorry, what's your name? Bhattacharya, presenting Proximal Graphical Event Model.
Hi, thanks. I'm actually Dharmashankar Subramanian, and this is joint work with my colleagues Devaran Bhattacharya and Tian Gao from IBM Research. So the title of our poster is Proximal Graphical Event Models. And so what they are, I'll try to tell you that in the next few minutes. The object of study in our work is multivariate recurrent event data. And so notationally, it looks like what you see at the bottom. You have an event data set where each arrival epoch in this event data set has a label, and that label lives in some finite set, say M types of labels, and you have several such arrivals on a common timeline. And applications are numerous, clearly. The objective that we have here is to learn an interpretable causal structure that somehow models the joint dynamics or joint dependence across these event types. And so to that end, specifically, we propose a certain representation of such event data sets called the Proximal Graphical Event Model. So what is a PGEM? It's basically a graph where there is a node associated with each event type, of which there are finitely many event types presumed in the data set. And every node in this graph can be thought of as a stochastic process. It's a point process. And the meaning of the edges in this graph is the following. Being a stochastic process that has dependence on other processes, the dependence is in terms of the conditional intensity function. And the conditional intensity function here is sensitive, or it depends on a proximal, as in recent history, of the arrival epochs of the parent event types. So the model is specified in terms of a graph and a set of parameters. The parameters are these proximal windows that is associated with each parent in the context of any child under question. So in this example, for process A, which depends on itself, it only is sensitive to the arrivals of its own type in a proximal window of size WAA, as in an immediate recent history. So it's a bit like having memory in the system, and how much memory is it that matters for the current instantaneous arrival rate of any process under question. And so the model is specified in terms of the graph and a set of window parameters, and corresponding to any parental state. So since you are sensitive to the occurrence of at least one parent, and there are multiple parents, so you'll have different combinations. So if you have two parents, you can have none of them, one of them, the other of them, or both of them. So as such, there are combinatorially many intensity parameters that capture the instantaneous intensity or arrival rate. So as such, it is a piecewise constant history-dependent intensity model. And so what does it mean for learning in this problem? There are two things to learn here: the parameters of the model as well as the structure. So given that we have a model, it's a stochastic process model, and we have data, once the model is specified with some relatively straightforward algebra, you can write down the data likelihood per the stochastic model that we have proposed. And that's what it looks like in the slide. So the main two things that happen here are that the timeline the common timeline over which you observe all the multiple event data arrival epochs, it partitions into a finite number of parental states in the context of any child process under question. So the optimal log likelihood is one that optimizes this partition. So there are two quantities here that matter: the number of times that the child process is observed in any given parental state, and how long does that parental state last over the entire timeline. So optimizing it is easy when you have knowledge of the structure as well as the parameters. When you have knowledge of only the structure, you need more work to get the parameters. And finally, you need some work to search over all possible structures. So here are some example results on synthetic data sets. The model performs competitively or better than comparable other models. And to learn more about it, I invite you to come to our poster number 6, room 210, 230 AB. Thank you.